So now let's go into the discussion of binomial distributions. There are several specialized variables that follow a binomial distribution, but for now let's just talk about what a binomial distribution is. So in a binomial probability experiment, each trial has a separate outcome, and it can only have two outcomes, hence the name binomial. So you can either be successful or failure. And these outcomes are going to be mutually exclusive. The random variable is going to be your number of successes in a fixed number of trials. So the probability of success is going to be the same for each trial, and the trials are independent, meaning that the outcome of one trial is not going to affect the outcome of another trial. And so you're going to use the number of trials n and the probability of its success to compute that binomial probability. A common example would be a young family has two children, both of them are boys. The probability of the third boy being a boy is still going to be 0.5 because the gender of the third child is going to be independent of the gender of the first two. So let's look at the formula for this. So the binomial probability function is going to take that combination formula that we talked about when we first started talking about with probability to calculate the total number of combinations that you can have, multiplied by p, which is your probability of success, raised to the number of successes, times 1 minus p, so that's the probability of failure, raised to n minus x, so that would be your number of failures. So your probability of success raised to the number of successes multiplied by your probability of failure raised to your number of failures. So that portion of the formula is going to be the probability of a very specific sequence occurring where you have X number of successes and N trials. So let's look at an example. So here we have Evans Electronics. They expect that 10% of their hourly employees will leave every year. So if we have 3 hourly employees at random, what's the probability that one of them is not going to be with us next year? So we have one outcome where we have leave, stay, stay. So the probability that they leave multiplied by the probability that they stay times the probability that they stay. And so if we go to calculate that, the probability of that one individual account occurring is 0.081. So the probability of leaving, 0.10 raised to the 1, because there's only one occurrence of that, multiplied by 0.9, probability of staying, squared, because there are 2 occurrences of that. So we have 2 other potential outcomes that we can have, right? Instead of just the first one leaving, maybe the second one leaves, maybe the third one leaves. And we didn't specify that order. So because of that, we need to add all 3 of those probabilities together to find out the probability that one of our 3 employees is not going to be with the company next year. We can also come to this conclusion by using a binomial probability tree diagram. So remember, leave is 0.1, stay is 0.9. You see that those probability values stay the same throughout, whether you're going from the first worker to the second worker or so forth. To get that total probability of that individual occurrence, you multiply using the multiplication rule the 3 probabilities together. So for example, if we look at the first worker leaving, the second worker leaving, and the third worker leaving, 0.1 times 0.1 times 0.1 is going to give me a probability value of 0.001, and my x is 3. But here my question is looking at what's the probability that only one of those 3 is going to occur. And so if we look at our tree diagram, we actually see that there are 3 occurrences in which we could only have 1 employee leave, just as we saw in the previous slide. And so once again, you take those 3 probabilities and add them together to get the same result that we saw on the previous slide. We could also use the function that we saw earlier in this presentation. So if we calculate the number of combinations, multiplied by the probability of success raised to the number of successes, multiplied by the probability of failure raised to the number of failures, we still find that we have a probability of 0.243 that 1 in 3 of my employees will leave. There's another opportunity that you have. We have probability tables. So if we look at the binomial probability table, if we were to choose 3, so that means my n is 3, what's the probability that one of them will leave? So that means my X value is 1. And we have a turnover rate of 10%, so we look for the 10. And so where those intersect on our binomial probability distribution table is once again 0.243. Now with the binomial probability distribution, we can find our expected value, also known as the mean, which is going to be your number of observations times the probability of success. Your variance is going to be your number of observations times the probability of success multiplied by the probability of failure. And then the standard deviation, once again, is going to be the square root of your variance. So let's look at this in the context of Evans Electronics. We had 3 employees with a probability of 10% turnover rate. So 0.3 employees out of 3 is my expected value. My variance is going to be 0.3 times 0.9, which is 0.27. And then my standard deviation is the square root of that, saying 0.52 employees. Now we also have cumulative binomial probabilities. So here we're looking at the Illinois Department of Transportation. They conclude that 76.2% of front seat occupants wore seatbelts. So that is both occupants in the front seat were using their seatbelts. So suppose we decide to compare that information with current usage, and we select a sample of 12 vehicles. So here, through using the formulas, the combination formula times the probability of success raised to the number of successes times the probability of failure raised to the number of failures, we end up with a value of about 9%. Okay? And the probability of selecting 12 cars and finding that the occupants of 7 or more vehicles, if we add all those probabilities together, was about 0.9562 or 95.62%. So when you can easily do binomial distribution calculations in either Excel or you can do them using the different tables, but make sure that when you're doing this, that if you just want the probability of a very explicit amount, you're looking at the appropriate table, because the cumulative tables will give you the values between 0 and whatever you're looking for. And so leading into that, there's a lot of statistical packages that will do this for you, but you can add the individual probabilities together, or you can use the cumulative probability tables, depending on what's easier to you and what makes more sense for you as you're solving the problems. We can use the normal distribution, which is a continuous distribution, as a substitute for a binomial distribution, which is a discrete distribution. For large values of n, because as your n increases, your binomial distribution is going to get closer and closer to a normal distribution. But first you need to make sure that the distribution that you're looking at really is a binomial distribution. So binomial distributions for an n of 1, 3, and 20 are provided here, where my probability of success is 0.5. And as our n value gets larger, you see that my shape becomes more bell-shaped or more normally distributed. And so calculating binomials for large sample sizes can be very tedious. So sometimes working with a normal distribution will involve fewer calculations and be more efficient. The continuity correction factor of 0.5 is used to extend the continuous value of x 1/2 unit in either direction. And this correction will then compensate for approximating a discrete distribution with a continuous distribution. And so this correction process is going to help to smooth the discrete distribution into a little bit more of a continuous distribution. So here we see an example, and we see that the example meets the conditions for a binomial distribution. We have a probability where it's the same for every trial. We have a set number of trials, and we want to know a specific number of successes. But however, it can be really time consuming to use that binomial formula on 60 cases. I'm sorry, 80 cases. And so the first thing you can do is determine the mean and standard deviation from that binomial distribution. Then you can use the Z formula to determine the area between the mean and whatever your, in this case, your X is 59.5. And then you can use 59.5 according to the first case listed on the preceding slide, saying finding the probability of at least X will occur using the area above X minus 5. And then, so 60 minus 0.5 is 59.5. And then you can use your Z tables to find a Z that corresponds with about 85. And we find, or 0.85, and then we see that that corresponds to an area of 0.3023. And so then we can calculate the area beyond 59.5 by subtracting 0.5 minus 0.3023 to get 0.1977. And this result is nearly identical with the binomial result that we would get of 0.197.